So the other day when we were talking about a desirability function, I said you take the individual desirabilities and you just multiply them times each other, and you have a 0 and a 1 here, and so you may have something that looks like this, and this will be multiplied times something that looks like this, maybe multiply something like this, right? And I said your desirabilities, it's just a linear function between 0 and 1, okay? Remember, desirability functions are conceptual, so there's nothing hard and definite about them. Another possibility is instead of using a straight line, you use an S-shaped function. So remember when we talked about logistic functions and sum of squares and that sort of thing? There's actually a very easy way to implement this. And the way you implement this is using the cumulative normal function. So for you guys that have had statistics, you remember this guy, the cumulative normal, okay? I mean the cumulative, or the normal function, the normal distribution. If you take the integral of this function, what do you get? You get this. This is called the cumulative normal distribution, okay? So it starts out at 0 and goes to 1. Now the good thing about it is it asymptotes at 0 and 1. So with desirability function, what you can do is instead of multiplying lines together, you multiply these inverse functions together. And it's really super simple to do, believe it or not. It's actually easier to do than linear functions given the capability of Excel, okay? So here's all you have to do. If I give you a population, some data, and I graph it, a lot of times it will have a bell curve. It's easy to calculate the mean for that, right? I just add up all of them, and I divide out by n, right? Now, how do I calculate the standard deviation? Well, the way I calculate the standard deviation is I take the sum of xi minus x bar squared divided by n minus 1. So this is this sum of squares we just got finished talking about a minute ago, okay? Okay, so you just add them all up, take the sum of squares, divide out by n minus 1. But here's the question I have. What happens if I just know the min of the function and the max, or the min and max, I should say, of the population? Is there any way that I can create estimates for my mean and for my standard deviation, my sigma, or sigma squared? Well, the answer is yes. For the mu, it's real simple. You just take max minus min divided by 2, right? Does everyone agree with that? So I take my max value, my min value, average them together, and the mean, if this is well distributed, well behaved, it's just going to be roughly in the middle of the two, right? Any ideas how I could calculate standard deviation?
We take the difference between the max and the mean and divide by 3.
Yep, that's actually it. Or you take max minus min divided by 6. Why 6? Because in statistics, you have these things called standard deviations. 1, 2, 3. And 3 standard deviations represent 99.73% of the data. So it's almost 100% of the data. So if you divide out by 3 plus and 3 minus, you get a total of 6. Okay? Or what Brett said, you could take just the min minus the mu divided by 3, which is
We don't give you halfway, they'll give you the positive and negative side, which could be identical.
It's the same thing.
They should be, yeah, exactly. So
If you look at your z-scores, I mean, they're identical on one side or the other.
So you could do mu minus min or mu minus max divided by 3, but you can just do max minus min, then that way you don't have to calculate the mu, okay? But you probably need to calculate it anyway, but they're the same thing, okay? So just from a min and max, you can calculate the mean and you can calculate the standard deviation, or you can get an estimate. which is all you can do anyway. I mean, if you got 2 data points, what else are you going to do with it? Now, so for the cumulative normal, here's all you have to do. If I have let's suppose I have a min of, I don't know, 40 and a max of 100. Well, what's halfway between these two? 70, right? So watch this. I'm going to come in here and I'm going to type in norm, N-O-R-M, dot INV for normal inverse. No, normal dist, I'm sorry. Normal dist. The x value, 70. This is what I want to know where it falls in the percentiles. The mean, well, I went too far. Let's go ahead and calculate, let's calculate the average, and let's calculate the standard deviation. And the way I'm going to calculate the average is I'm going to say min of these two, no, I'm going to say max of these two, I'm sorry, max of these two minus min of these two divided by 2. And that should be what, 70? Okay, what did I do wrong here? No, it's not difference, it's add. Right, there we go. Right. Now here I'm going to say, now this is the difference, I'm sorry. The max of these two minus the min of these two, right? And I'm going to divide out by 6. So the standard deviation is 10, which, let's think about it. Okay, well, yeah, that kind of, I mean, that's 3 standard, because each standard deviation is 10. So, I mean, it makes sense, right? So now I'm going to do I'm just going to say the area. So I'm going to go norm.dist, this value here, which is my value of interest, the mean, which is this value, the standard deviation, which is this value, and I put a 1, which is for true, that I want the actual cumulative value. So there we go. So I plug in a 70, I get a 0.5. Let's suppose I plug in 50. What do I get? 0.22 or 0.022. So let's suppose I plug in I don't know, 55. What do I get? Let's suppose I plug in a 40. What do I get? I almost get 0. Not quite, but I almost get 0. If I plug in 100, what do I get? Almost get 1. So do you see how this naturally bounds between a 0 and 1 for me? It's like, but it's not perfect. Okay, it's not perfect. It's all 0.0013. Okay? Put in a correction factor if it really bothers you that much. So in theory, the highest desirability you're going to be able to get is a 99.865, which is nearly indistinguishable from 1. Okay? That makes sense? All right, so I can either...
Statistics so easy.
What'd you say?
That would have made statistics so easy.
Just dividing out. Yeah.
Instead of having to do your standard deviation by hand, longhand, like arguments.
Right. You just rough it. Yeah. That's what the early. That's why you have R charts in statistical process control, because years ago, I mean, an S chart is actually, I don't know that it's any better.
We had all kinds of downtime before we were on the Mayflower.
Yeah. Well, an R chart, though, all you have to do is take the difference. And so you just plot that. So your control charts, that's why they used R charts years ago. Now you're starting to use S charts because you can actually use the computational power of the computer to calculate standard deviations. Go back 60 years ago and take 100 data points and calculate the standard deviation. Good luck with that, because you got to do the sum of squares. Then you have to divide out by n minus 1, and then you have to take the square root of that. Or you could just go through, oh, this is the max value, this is the min value, and I'll divide out by 6. And it's like, oh, but you're off by like, 0.021. It's like, okay, big deal, I'm off. It's statistics anyway, okay? So does everyone see, though, the rationale of how this naturally gives you a value between 0 and 1? So you can either have what's called larger the better. So, the larger the value is, the closer it gets to 1. Smaller the better, so the lower the value is, the closer it gets to 1. Or target the better. So whatever the value is, it goes up kind of like a parabola. Now you may be saying, man, I bet this one is hard to calculate. It's actually super simple. All you have to do is take this guy and multiply it times this guy. And then you just shift the means. Because if you think about it, anything left of this value is 1. What's 1 multiplied times anything? Anything. Right. Anything to the right of this is 0. What's 0 multiplied times anything? 0. So the way you calculate this target the better is you just multiply you multiply a smaller the value, smaller the better and larger the better together. So like if I change this min to say like 80, watch what happens. See how it's kind of skews this out, 70. And so this is super simple. And then what I do is I end up dividing this value out by a correction factor, which is just the area, the maximum area squared. And this is 0.997, okay? And so when you do that, you're able to actually get a desirability of 1 up here, because that maximum value is going to be like 0.997, but I divide out by 0.997, and so that's 1, okay? But even if you didn't do that this number is still going to be very close to 1, all right? So I'm going to show you an example of where I solved this using my normal distribution. And the answer that I got when I solved it using desirability is I got a 0.669, okay? When I used the normal approach, I get a 0.763. But look, this is what's interesting. When I compare these two answers, remember this value, this is 0.669, and I paste this value in, it's very close, okay? And vice versa. You might want to use this approach compared to a linear approach for one reason, is in general you will get a higher desirability. And the reason why you will get a higher desirability is because if this were a linear function, it just goes from point A to point B. But once you get past this midpoint, see how this grows more quickly than if you just had a line drawn through here? So if you just had a line from point A to point B, once you got past this midpoint, you'd be growing through this area. Whereas here, you're kind of on this exponential. So in general, these numbers will appear higher, even though the answers aren't any different, okay? So you may say, well, who cares? Why? Well, when you're presenting this to people, yeah, when you're presenting this, someone may look at this and say, oh, wow, 65, that's actually not that good. I mean, surely we can do better than a 65. And then you say, no, but that doesn't really mean anything. This is just, it's conceptual. 65 doesn't, it's just, that's a 65 out of, oh yeah, but a 65. I mean, would you be happy with a 65 on a test? Well, no, but the 65 doesn't really mean that much. It's just a conceptual measure. Well, I don't want a 65. Surely we can do better than a 65. I think you need to get back to work, sort of thing. Whereas if you're using this approach, you can take advantage of this nonlinearity, and the answer will actually look better. So now it's like, oh, we scored a 76. It's like, well, 76, that's actually not that bad, you know. and you have to be aware of this, because you think I'm kidding that you come in and you have a desirability of a 0.46, and you say, look, I mean, that's not the, you know, 46 isn't all that great, but that's the best we can do with this system. So you have to realize that 0.46 represents the best that the system will give us. So it's not about me going in and working harder or doing a rearrangement and being able to get a better number. This is just the best it can do. Whereas if that 0.46 all of a sudden magically becomes 0.67, then it's like, oh yeah, okay, well that's okay. And you may even want to go in with these numbers and you know, do some funny money and divide out by correction factors to get those numbers higher for presentation purposes. And the reason why I tell you this is because if someone doesn't understand this field like you do, sometimes they take these numbers to mean something literal. And it's like, no, it's just a conceptual measure. We just had to use a proxy objective function to to optimize something. Okay? All right. And I'm almost done. One of the things that I want to show you, though, that is something really cool, um, is what's called a user-defined function. Okay? So the cool thing about Excel is you can actually go in and if you need the data to do something and there's not a function, well, one, you can use VBA and write a program, but you can make your own function. So what I did here is I used this, I created a function, it's just called LTB, which is larger the better, and you go in and you put your minimum value, let's suppose I put a value of 40, your maximum value is 100, and then whatever value that you're evaluating, and see how it gave me a 0.5? So instead of me actually having to write all these functions and link these cells, all I have to do is go in and I made my own my own function. So I just call it public function, lower the better, LTB, so Excel will recognize it. Lower value, upper value, whatever the value is. I used the norm dist function, which is built into Excel. I put the value in. I take upper and lower divided by 2, which is the mean, or upper plus lower divided by 2, which is the mean, upper minus lower divided by 6, which is the standard deviation, put a 1 there to make it cumulative, and I just magically made my own function. Okay? And you could do that with anything. You could actually go in and, you could do something like this. You know how you guys are calculating, like I had you calculate the distance for the optimal facility location. So I have you calculate like distance here, and then, you'll have a value of something like this, and then you have to sum them up. You could have a sum distance function to where all you would have to do is have some x, y values here. You type in like, it doesn't exist, but you could type in like some distance or whatever you wanted to call it, drag all of these values. It's not going to work because the function doesn't exist, and it would just sum up those distances for you.
That's pretty slick.
Or you could have it do something like, for instance, the traveling salesman problem, where I showed you those heuristics, like a 2-op and a k-op, or you swap things out. You could just have it come in and you just pick all of these, and it goes in and uses a heuristic. So you could have something like, I don't know, you could like short, let's suppose we called it short TSP, okay? And then you just grab all of these. It goes in, runs it through a heuristic, it may take it a few seconds, figures out what that shortest path is, and then outputs it. And then that, in of itself, could be a function inside of Excel Solver. So in that sense, you can have nested optimization problems. Okay? So you can really get into some really cool things that you can start doing with these functions. So this class isn't on Excel, but there is so much power built into Excel that the average person has no idea about. Okay? Now I'm going to wrap up, and the class will then be over. Okay. Do this real quick. PowerPoint to wrap up. Only 3 slides. And maybe I didn't. What did I do here? Oh, okay. There we go. Okay, here we go. So I'm going to give a wrap up for the class. All right, this is going to be very simple. First of all, OR is a field. I want you to be aware that this class, as with any introductory OR course, is only the tip of the iceberg when learning OR concepts. There are many, many topics left to be covered in the field, and new and innovative techniques are constantly being developed. So this is a very active area of research, and the reason why is because it's just important, okay? There's a lot of research that is going into like learning networks and artificial intelligence, but at the end of the day, all of these algorithms and approaches are trying to optimize something. Usually it's an error function. So when you talk to your phone and it's transcribing text, what it's really trying to do is minimize the error, minimize the number of mistakes it makes. When you type in a search into Google, it's trying to minimize the number of times it finds something that you're not looking for. You know, the game of chess is trying to minimize the number of times it loses. The new game of AlphaGo that plays the game of Go is trying to minimize whatever the objective function is. That's what life is, it turns out. You know, I sum up life as essentially we're trying to minimize our energy expenditure. That's what really almost all organisms do. They just try to get by with doing the least amount as possible. Okay? Um, so here's what we've covered, and here is just the tip of the iceberg. You know, quadratic programming. We didn't cover dynamic programming, duality theory, traveling salesman. We got into it, but we didn't get into any of these heuristics. The field of computer science is actually a subset of OR. Queuing theory, Markov chains, interior point methods, approximation methods, nested optimization, meta-heuristics. You could teach an entire course just on the concept of meta-heuristics, hybrid algorithms, sequential quadratic programming, sequential programming, I think is what it's called, where you basically you take a quadratic function, you break it into a bunch of lines, and turn it into a linear function. Then you can solve it as a linear programming problem. And the list goes on and on. Down here at the bottom, I put artificial intelligence. I think in the next decade or so, artificial intelligence is going to make its way into OR, and it's going to revolutionize the field in a way that I probably can't even begin to understand. But it's already starting to make inroads to where you put these learning algorithms on these functions, and it just figures out what the best answer is. It's like, how does it do it? It's like, I don't know how it does it. It just does it. Okay? So some advice when dealing with OR. Don't be stupid. Okay? So seriously, don't do that. Okay? Use some common sense. Mathematics will only give you so much. Many times decisions require the human element. So the math will only give you so much. You have to have the human element. Know when to stop. So look at yourself as part of an optimization problem where you're either trying to minimize time or minimize cost expenditures. So your decisions themselves are part of an optimization process. If it costs more money to formulate and solve a problem exactly than what a quick heuristic will give you, you may be better off with a good solution than an optimal one. So your example of light placement is a perfect example. It may be the optimal place to place lights, but we just spent half a day trying to figure that out, and we could have already had the light fixtures up. So you're part of the process in and of itself. And I'm going to rail for just 10 seconds. This is part of the problem I have with our judicial system, is the judicial system doesn't see itself, literally, as part of the process. It's like above and immune, and I think that is one of the problems that we do have in society, that it's able to separate itself and say, money, time, oh, those are no big deal. Oh, they're not an issue. It's like, yeah, they actually are. And so that's an example where I see a system that kind of removes itself, you know, it wants to be an exogenous variable, but it's like, well, you're actually in the system itself. So look at yourself like that also, that I'm part of this process, and if I'm spending a lot of time and a lot of money trying to optimize a process, then I may not be looking at the meta level, okay? And be aware that a better answer always exists. You'll probably never, ever get the absolute best solution to a problem, so many times you have to satisfy, sacrifice, and satisfy, and so you give and take a little. And that's pretty much what I wanted to cover in this course. So I hope you got something out of it. I hope that when you go forward in life, even though you may not remember all these exact concepts, that you look at the world. You know, my goal was when we started this class, I wanted you to end this class by looking at the world a little differently. You know, the details you'll forget, but everything you look at it, at least that's how I view the world now. I'm always looking at it Jeff Bolton and I will say that. You look at it, your brain goes, it's like, all right, I found either I converged on a solution or it's tending off to infinity and the machine's getting ready to blow up. So anyway, are there any questions with the class? Okay. Well, if not, I will post exam 3 maybe today, maybe tomorrow. Yeah, the final exam, and give you guys time to work on it. It won't be that bad. I want to try to give you guys a break because we actually have covered quite a bit before, so I'm happy with what we covered so far. All right. Well, it was a pleasure having you in the class. If you ever have any problems or anything you need help with, you know where to find me.